Swayam Prabha. Digital India. Educated India.
Let us continue our discussion on crystal structures. We have already discussed the simple oxide structures and some alkali halide structures. Let us go to little bit of complex structures, and to start with we will have a fluoride structure, what we call fluoride structure. Once again, just like sodium chloride structure, it is called the rock salt structure. Fluoride is also a mineralogical name of calcium fluoride, CaF2. Okay. So, the fluoride structure can also be described more or less in the same fashion. Of course, the unit cell is little complex, but one can discuss more or less following the same principle. Here fluorine is a cation, the anion, and calcium is the cation. Calcium has a smaller size compared to fluorine. If you look at this structure to start with, you will see fluorine ions being larger ions, they form the skeleton and forms a cubic symmetry. So, it is once again a cubic symmetry, just like sodium chloride structure, where chlorine ion forms the skeleton of a cube, and but unlike sodium chloride, sodium do not go to the octahedral side, or calcium do not go to the octahedral side. Its size is slightly bigger than sodium, and therefore, it does not go to the octahedral side, but it goes to the body center position. Here it is the calcium ion. So, it is actually a body center position. Now, if you go to the body center position or body center structure, BCC structure, you will find the contribution of the fluorine ions to this particular unit cell is 1/8 into 8. That gives you 1 fluorine ion, and the calcium being at the center of the cube, it not shared by any other neighboring unit cells. So, its contribution to this particular unit cell is also 1. So, if this particular unit cell is repeated in the volume, then the fluorine is to calcium ratio should be 1:1 in the compound. However, we have a different molecular formula CaF2, that means there are double the number of fluorine ions compared to the calcium ions, and that gives a different kind of situation. So, that in the cubic structure, when you try to repeat them one after the other, then it can be described in the following manner. Calcium ion do not sit in all the cubes. Okay. In this particular example, we have seen the calcium ion is sitting at the center of the cube formed by the fluorine ion. Unfortunately, what will happen in the next neighboring site or next neighboring unit cell, the calcium ion will be missing, it will be vacant. So, that each alternate cubes have a calcium ion. So, calcium ions are not in all the cubes, only in the alternate cubes, whether you go in the x direction, y direction or z direction, right. So, that is the structure, and that has been seen, that has been demonstrated in the left figure here. So, this is not the unit cell, this is the part of the unit cell, whereas this complicated looking structure is actually the unit cell. So, chlorine calcium ion are not always at the all the corners or all the body center positions of the cube, but it is only in the alternate cubes. So, it says here the fluorite CaF2 structure is named after the mineral calcium fluoride CaF2. The structure may geometrically be considered to constitute a closed packing of the metal ions, while the anions occupy all the tetrahedral sides. You can, this is a different description than what is been given here. Okay. Here it says the calcium ion is larger and fluorine ion goes to the tetrahedral sides. The calcium ions are smaller than the fluorine ions, and the fluoride ions are thus not able to fit into the interstices of the calcium ions. The structure can also be viewed as a simple cubic packing of the anions, not close packed within the cations, with the cations occupying every second or the alternate cube void. That is what the description I gave you just now. This is the second part of it, but the structure can also be viewed in a slightly different way, because this is an one exception situation where calcium ion is a much bigger than the fluorine ions. Okay. So, normally anions are bigger than the cations. Here the cations is slightly bigger than the anion, and as a result anion goes to the interstitial sites. That is one way of describing the structure. The same structure can be viewed in different ways. Anyway, so this is the particular way you can describe the arrangement of calcium and fluorine ions in a calcium fluoride structure. Now, this is what we call a structure type. There are many compounds, several compounds which actually crystallizes in this particular structure. One of the very important characteristics of this kind of a structure is that since calcium ion is sitting on alternate sides and alternate sides are vacant. So, there is a channel kind of through the structure, there is a lot of void space, and that void is not distributed, is along a particular direction, and these void spaces are become quite important for ionic mobility. Okay. Sometimes these voids are beneficial for the movement of the ions, where if you heat these materials at a higher temperature, then atoms can move through these voids. We will see later on how the atomic movement takes place and what is the role of crystal structure or imperfections. Crystals are not always perfect, there will be always some imperfections, and that is the rule of the game, and that is imperfections are much more common than having a perfect crystal. It is almost impossible to get a perfect crystal, but imperfections are always there. We will discuss part of it at a later class. So, in addition to that, the structural features are also important for the movement of the cations or movement of the anions in this particular case. So, we will discuss that when we will discuss the property. So, that property is actually derived from this particular typical critical structure. Now, as I said, it is a structure type, fluoride structure type, and some of the important oxides which crystallizes in this particular fashion or in this particular arrangement are zirconium dioxide, cubic, particularly the cubic form, cerium dioxide and TiO2. You will all find that the cationic to anionic ratio is always 1:2 in all these oxides, as in CaF2. Okay. So, all these have a particular structure, and they have also some common characteristics, common property characteristics. We will discuss that later, and you will find that these oxides, because with the structural similarity, they have certain similarity in electrical properties in particular. Now, we have mentioned here zirconia cubic, because many of these oxides do have different polymorphs. That means at different temperatures, I mentioned in an earlier class that iron has different polymorphs. At low temperature it has a BCC structure, at higher temperature above 900 degrees it has a FCC structure. Similarly, zirconia also has different structures. Zirconia have different arrangements of atoms at different temperatures. At room temperature it has a monoclinic crystal structure. So, the CaF2 structure is not valid, although the chemical composition is same, but the structure is different. We will discuss that maybe at a later stage, how the polymorphic changes takes place in zirconia, and that is the reason we have mentioned that zirconia in the cubic form, when it is particularly in the cubic form, and that is a very high temperature stable form above maybe 2500 degrees centigrade, zirconia has a cubic polymorph, and that has this fluoride structure. That is not so in case of CEO2 or TiO2 thorium oxide. CEO2 throughout is a fluoride structure, same is the case with thorium dioxide. Next we come to another structure, once again the similar molecular formula. This was CaF2, but this is TiO2, and one of the polymorphs of TiO2 is called rutile structure. This of course is not a cubic structure, incidentally it is not a cubic structure. All so far we have discussed only cubic structure, but this is a deviation from the cubic structure, and a rutile structure has its name from the rutile modification or a particular structure type of titanium dioxide TiO2. It is based on a hexagonal closed packing structure. It is not a closed pack structure although, okay, but it has certain similarity with the hexagonal symmetry. In fact, the symmetry is basically a tetragonal symmetry. While titanium ions occupy every second octahedral void. Okay. Here again we come back to an oxide, and so the titanium ions or the metal ions or the cations are much smaller than the oxygen ions. So, they go to the, and the radius ratio is such that it occupies octahedral side rather than tetrahedral sides. So, titanium ion goes to the octahedral side. So, the structure can be viewed as consisting of TiO6 octahedra. So, there are 6 oxygen surrounding a titanium ion. So, that is a preferred coordination number for titanium, particularly titanium 4 plus, and then that octahedra slightly distorted. It is again not a very regular octahedra, it is not a symmetric octahedra, it is distorted, which share edges and corners in such a way that each oxygen atom belongs to 3 neighboring octahedron. Okay. We have seen earlier in case of a cube, the corner atoms, corner oxygen or corner atoms share 8 unit cells. Here they are belonging to shares 3 neighboring octahedra. The structure is tetrahedral, and when the structure is viewed along the C axis, it may be seen that the structure contains channels along the C axis. Once again it has this channel in a particular direction means that basically they have an anisotropic property. That means in different directions they will have different properties because they are not symmetric completely. So, it has certain anisotropic property along the C direction, but this is the symmetry is basically tetragonal. Okay. So, these are titanium ions at the corners, and oxygen actually surrounds or titanium ion is surrounded by 6 oxygen, although this is a different description. You see, one has to remember that according to our convenience we describe these structures sometimes the cations at the corners or anions at the corners. We have seen earlier that most of the cases the cations or the anions we put in the corner position, but here the cations or the titanium has been put in the corner position. Rest of the description is not that important, but except that it has a tetragonal symmetry, and titanium has a octahedral coordination. Okay. So, most of the time it is not the symmetry only which is important, particularly for complex oxide. You will find symmetry is not always very important. More importantly, we need to know what is the coordination number of the cations involved, or what is the coordination number of the oxygen. That means, how many cations are surrounding an oxygen ion and how many oxygen is surrounding a cation. So, this is the way we normally describe the structure of some of the oxides. There are quite a few oxides which crystallizes, which has this TiO2. Once again, this is a structure type. Okay. It is a rutile structure. So, if you have to say that what is the structure of MnO2, one can very easily say it has a rutile structure. That describes everything. Okay. You do not have to go to the description of the symmetry, description of the position of the ions, position of the cations and the anions. You do not have to do it, because they are identical. So, SnO2 just like TiO2 is a rutile structure, MnO2, VOO2, molybdenum dioxide, ruthenium oxide, germanium dioxide, all of them have this particular structure. Their lattice parameters may be different, of course, their exact distances between the cation and the anion or two cations may be different, but basic symmetry remains same. So, that is how one can always describe the structure of an oxide or other compounds as well. We go to another type of structure, which is a very important structure incidentally, and it is a very important compound as such, aluminum oxide. And the mineralogical name of one form of aluminum oxide, that is called the alpha aluminum oxide. There are alpha, beta, gamma aluminum oxide is also there, having a different crystal structure. It is more of a cubic structure, and in this case alpha aluminum oxide, which is the most common variety of aluminum oxide, and the mineralogical name for that is corundum. So, this is the structure of corundum, in which oxygen ions are arranged in again HCP. So, symmetry must be also known, and then the coordination number of the cation and the anion should also be known. That is how actually we describe the structures. So, it is a corundum structure in which oxygen ions are arranged in HCP and aluminum ions are in the octahedral coordination once again. Now, in an HCP structure, we have seen earlier whether it is HCP or a closed packed structure or a FCC structure, the face center cubic structure, both of them are closed packed structure, and there are as many number of octahedral sites as there are oxygen sites. Okay. So, if oxygen creates a HCP structure, so the number of oxygen in an unit cell will be the same as that of the number of octahedral sites, because we have seen earlier the number of octahedral site and the number of anions are same in FCC structure. Same is the case with the HCP structure, because both of them are closed packed structure. They are identical structure, except as we discussed earlier that there is a change in stacking. One is ABC stacking, another one is AB stacking, but otherwise they are identical. So, the number of octahedral sites available to us will be the same as the number of oxygen ions in a molecule. So, the compound has a molecular formula which is Al2O3. that means number of cations to the number of anions is 2:3. Now, if you have same number of octahedral sites as that of oxygen, the basic, which forms the basic skeleton, then the molecular ratio should have been ALO, but it is not. The molecular formula is Al2O3. Therefore, the number of aluminum ions occupying the octahedral sites are actually 2/3, okay, because the ratio is 2/3. So, 2/3 of the available octahedral sites are actually occupied by the aluminum ions, whereas 1/3 is remain vacant. So, that is another very important feature of corundum structure, in which it is basically a hexagonal closed packed structure, where aluminum ion goes to 2/3 of the available octahedral sites, and all the tetrahedral sites, because any closed packed structure will have two types of interstitial sites, octahedral site as well as tetrahedral sites. Aluminum goes to the tetrahedral site, but that is the it satisfies the conditions of the radius ratio of the octahedral sites. So, it does not go to the tetrahedral site. Okay. So, all the tetrahedral sites remain vacant, whereas only 2/3 of the octahedral sites are occupied by the aluminum ions. So, that is how one can describe the corundum structure, and otherwise it is, although it looks quite complex, there are bonds between the cation and the anion are being shown as in any other structure, but they are basically, for example, here you can see this is the aluminum ion and it is surrounded by 4 oxygen ions in the octahedral form. So, all the aluminum ions which are shown here are actually surrounded by 6 oxygen ions. Now, these are also surrounded by 6 oxygen ions, but some of them belongs to this unit cell, others will be belong to the neighboring unit cell. So, the aluminum ions which are sitting on the edge are actually surrounded by some oxygen ion of this particular unit cell and few others from the neighboring unit cells, but all of them will have octahedral coordination, and whatever available octahedral interstitials are there, only 2/3 will be filled up. So, that is how one can describe Al2O3, and there are quite a few oxides which are have this structure. Okay. So far we have been discussing only simple oxides, where only there are one type of cation present, okay, either barium, strontium or aluminum. So, there are simple oxides, what we call the simple oxides. Now, we go to another group of oxides which are normally referred to as complex oxides. That means, oxygen of course, is the only cation in all these oxides, but all the oxygen is the only anion present, but the cations may be more than one. So, this is one such compound is called AbO3, that is the general formula of the compound, where A is basically a divalent ion, A is divalent and B is tetravalent, okay, like this. Okay. And the perovskite is called the perovskite type, just like fluoride is calcium fluoride and rock salt is sodium chloride. Calcium titanate has a mineralogical name called perovskite, and it is a very important group of compound, very important group of mixed oxides which have many different applications and many different properties. Later on we will see that. So, we must understand what is this, how do we describe the atomic arrangement in these kind of compounds. So, calcium titanate, where A is the calcium the general formula of these all these groups of titanates, there are titanates, tannates and so on. So, one of them is a alkali metal oxides, okay. Calcium is divalent. So, it can be replaced by barium, it can be replaced by strontium and so on. Magnesium, other one is titanium 4 plus, okay. So, 2 plus plus 4 plus and then it is 3 minus 2 minus. So, what is the description? Description is well relatively simple. Once again, it is a cubic symmetry. First of all, it is a cubic symmetry, not hexagonal symmetry, it is a cubic symmetry. And calcium and oxygen, we have seen earlier, calcium, the size of the calcium is fairly large, okay. Size of the calcium is fairly large, and that is the reason with fluorine it is more than fluorine, okay. So, the calcium is very close to that of oxygen, and therefore, if when we are talking about a cubic symmetry, both calcium and oxygen together forms the cubic symmetry or a closed packed structure. If you look at this particular part of the diagram, you will see these are calcium, the dark ones are calcium, lighter ones are oxygen. So, these are oxygen, or it can be reversed also. In this case, I think this is oxygen, these dark ones are oxygen and these are calcium, okay. The lighter ones are actually calcium, it is not somehow not written. So, this is your titanium. Titanium sits at the center of the cube, okay, body center of the cube here, and these are oxygen. Oxygen are on the face center of the faces of the cube, and corners are occupied by the calcium. So, calcium goes to the corner, oxygen goes to the face center, and titanium goes to the body center of the cube, and that is how titanium is 6-fold coordination, okay. Titanium has a 6-fold coordination, and calcium are at the center. Now, that is why in the bottom you can see this is the 6-fold octahedron, okay. It is a bipyramid kind of structure. This is a square pyramid, the base is square. So, you have 4 oxygen ions, one on the top and one on the bottom, okay. That is how it forms the octahedron. So, that is the typical structure of an octahedron or regular octahedron. It can be distorted also in some cases. So, that is the description of calcium titanate, and this has been represented in this manner, in a slightly different manner, but the same structure is there. So, more or less it is the same thing. Occupy, you can see the description is also given, titanium 4 plus occupy the body center position, which is in octahedral coordination, okay. There are a few more diagrams. Here, instead of earlier we have seen 2 layers, here is a 3 layer. So, this is 1 unit cell, this is another unit cell, and this is a 3 unit cell. So, this is repeated here, you can see the octahedron, this is another octahedron and then octahedron. So, Ti 6 minus octahedron, or you can written here as a polyhedron. So, these are oxygen ions at the body center, the corners are calcium, and titanium is a much smaller ion, much smaller than both oxygen and calcium. So, they goes to the octahedral site. Okay. Once again, all the octahedral sites are not occupied. Okay. There are as many as 6 octahedral sites, 4 octahedral sites in this structure, but only one of them is occupied, rest are remaining vacant, and all the tetrahedral sites are also remaining vacant. So, that is another way of looking at it. So, there are a lot of voids, there are voids present in the structure. Yes. Although oxygen and calcium are in close packed position, but rest of them are really voids. Another very important structure is called spinel structure, right. The formula just like AbO3, here the compound is slightly different, it is Ab2O4, Ab2O4. So, it is again a compound of two different oxides, one is AO, another is B2O3, okay. One is AO, another is B2O3. So, together forms Ab2O4. So, A is a divalent metal, B is a trivalent metal, and then oxygen. Okay. So, there are large number of compounds in this spinel structure also. In fact, perovskite and spinel, there are huge number of compounds available in this particular structure. Now, the description is like this. These are A cations, okay. Red ones here is A cations, small cations in oxygen tetrahedron. So, once again it is a cubic structure in which both tetrahedral sites and octahedral sites are available, and both of them are occupied, may not be fully, but at least to a certain extent. So, you have two different metals, one is A and another is B, and well, to be specific, A can be magnesium and B can be aluminum. So, it has become magnesium oxide and Al2O3, MgO Al2O3 or MgAl2O4. This particular compound, just like calcium fluoride, has a mineralogical name which is called fluorite, or sodium chloride has a mineralogical name like rock salt. Here magnesium aluminate has the mineralogical name spinel, and that is the reason the structure type is called spinel. Oh, I forgot to mention that perovskite is the mineralogical name of calcium titanate. Okay, that is the reason calcium titanate as a structure type, and that is known as spinel, that is known as perovskite, whereas magnesium aluminate the mineralogical name is spinel, and that is the reason this particular crystal structure is called spinel structure. There may be many compounds having this particular structure. So, once again coming back to the description, here both octahedral and tetrahedral sites are occupied, partly, not fully, partly occupied, and A site or A cation, in this case the magnesium goes to the tetrahedral site. So, magnesium ion has a 4-fold coordination, whereas aluminum we have seen earlier in case of Al2O3 or corundum structure, that aluminum has a 6-fold coordination. So, aluminum prefers to go to the 6-fold coordination all the time in any compound, except in certain, there are exceptions of course, but normally aluminum goes to the octahedral side and magnesium goes to the tetrahedral side, which also indicates that the cationic size of the or the ionic radii of the magnesium is much smaller, and that of aluminum is larger. So, that is what it is also mentioned here, that smaller cation goes to the tetrahedral side and larger cation goes to the octahedral side. Now, here in this structure looks little complex, but actually there are 8 units of the cube. If you look at carefully, they will find out 8 units of the cube. Okay. So, in the structure or in the spinel structure there are again two kind of varieties or two kind of types, two types of spinel structures are available, not one type. This is one type where we have said that all the A ions goes to the tetrahedral side and all the B ions goes to the octahedral side. In this is what is called the normal spinel. MgAl2O4 is actually having a normal spinel structure, and that is also called normal spinel. There is another variety of spinel structure which is called inverse spinel structure. Inverse spinel structure in which there is a redistribution, of the cations, the two types of cations which is present, A and B cations. So, B, particularly the B cations which are larger cations are normally goes to the octahedral sides. In an inverse spinel structure the situation is slightly different. In the inverse spinel structure half of B goes to the tetrahedral side, okay. Half of B goes to the tetrahedral side and half remains here. So, in an inverse spinel structure actually all the A cations remains in the tetrahedral side, but part of B also goes to the tetrahedral side, and that is because some of the cations in some of these situations, some of the cations actually have a borderline situation so far as the radius ratio is concerned. Radius ratio is such that they can go to the octahedral as well as the tetrahedral side, okay. And therefore, those structures are different from the normal spinel structure, although the basic consideration is same, but if you go to the details of the structure there will be some difference, and that is very important, and that particular redistribution of some of these cations give rise to many interesting properties, particularly when you talk about magnetic properties. Okay. In fact, it is this redistribution or the inverse spinel structure which is important for magnetic properties. You will find when B cation is iron, and iron can have two different valence states. Okay. So, one is 2 plus, another is 3 plus. Iron of course, in this case it will be 3 plus and Fe2O3. So, that whenever the Fe2O3 is there, then that spinel structure will have a inverse spinel structure. Okay. One example is, for example, here you can see the manganese, nickel, cobalt and iron. Okay. Manganese 2 plus, nickel 2 plus, cobalt 2 plus, and iron it can both has 2 plus as well as 3 plus states. So, that way iron can be present both in the tetrahedral side and in the octahedral side, whereas these are normal spinel. When zinc is there, that is a normal spinel structure. Zinc, these are also 2 plus, these are also 2 plus. Okay. So, it is actually A cation, A is a 2 plus. Okay. So, when zinc is A is zinc or magnesium or barium, they go to the tetrahedral side, whereas these ones also goes to the tetrahedral side, but part of the trivalent ion also comes to the tetrahedral side, and that is why this Me 2 plus oxygen, that is AO, and B2O3, B is 3 plus. when these things, this one of the compounds is Fe, that is called ferrite. Okay. So, the ferrites has another, they are not from the point of view of the crystal structure, their point of view from their properties. So, ferrite Fe2O3, when B2O3 is Fe2O3, then that compound or that spinel compound is called ferrites, and ferrites normally has inverse spinel structure, right. Part of Fe3 plus remains at the octahedral site and part of it, half of it goes to the tetrahedral site, and that is how it creates a magnetic property very important for many different applications. So, the ferrites do have a inverse spinel structure, but aluminates that means when the B cation is aluminum, it has a normal spinel structure. Chromium can also have both structures, both inverse spinel as well as normal spinel. So, depending on which particular cation you are getting involved in the compound, the structure will change. Okay. So, that is what is the description of the spinel structure, and it is quite, both perovskites and spinel are very important structures so far as the oxides are concerned, and we will see later on that many of the properties are depend on this particular structure type or the description where exactly the cations are present. Well, having discussed all the different kind of some of the oxides, let us look at one of the very important oxide which is very common for ceramic materials, that is silica, SiO2. Silica, just like aluminum oxide, is a very important constituent of ceramic group of materials. So, let us try to look at what is the silica compound, silica SiO2, and what are the different compounds based on silica. In fact, there are a large variety of silicates, because silica, pure silica is also available. So, that is a important constituent of glass making. In addition, of course, it gets combined with many other cations or many other oxides and forms many different kind of silicates. These silicates are very important raw materials for ceramics, particularly traditional ceramic materials. As we have discussed earlier, that traditional ceramics, most of the traditional ceramic raw materials are naturally occurring, and they are some form of silicates. Okay. Silica is one of the major constituents. In addition to silica, of course, there are many other cations, sometimes they are quite complex structures, and in addition to other cations, there may be some hydroxyl ions. So, in fact, many of the silicates do have a hydroxyl ion present there, and that determines some of the very important surface property of silicates. In fact, one of the properties of silicate is the plasticity, and because when you mix with water, it forms a kind of suspension, and that suspension, depending on the amount of the water, you can have a good stable suspension, or you can have a plastic mass. You can deform those materials. Their presence of water actually makes the material more plastic, not in the completely dried form, but when it is present in the in presence of water. So, silicate structures are very important for the traditional ceramic raw materials. So, let us try to look at some of the structures available to us. The basic consideration of silicate structure is what we call the SiO4 tetrahedron. Silicon in presence of oxygen forms a tetrahedral coordination, four-fold coordination. It is a very important tetrahedron so far as the oxide structures are concerned. So, the basic building block in most of the silicates, almost all silicates, is this tetrahedron. silicon as the center of the tetrahedron, and it is coordinated by a regular tetrahedron consisting of 4 oxygen ions. Silicon, the cation size is much smaller compared to oxygen, and it forms a kind of molecule, right, a kind of molecule like this, or some kind of an complex ion. So, if you have SiO4, SiO4, Si is 4 plus, it is a tetravalent cation, and oxygen is 2 minus. So, you have actually net positive charge of 4 minus. So, all silicon oxygen tetrahedron has a 4 minus negative charge, some kind of a complex ion. So, if this 4 positive charge has to be 4 negative charge has to be satisfied by combining with other groups, and that way it can have many complex structures. Now, when 2 of such units are joined together by a common oxygen, okay, this particular oxygen is common to this tetrahedron and also the other tetrahedron. So, this is a common oxygen between 2 neighboring tetrahedrons, right, and this is what we call a bridging oxygen. It bridges between this tetrahedron and the other tetrahedron. So, it is also a very common phenomena in any silicate structure, that there are presence of bridging oxygen and non-bridging oxygen. We will come to that later on, but mostly when a oxygen is common or the oxygen bond is satisfied, one bond, one negative charge is with this silicon and another negative charge is satisfied with this silicon, then it is a bridging oxygen. There is no extra negative charge sitting on this, whereas these are non-bridging oxygen. These are non-bridging oxygen because some other cations can be can join or can combine with this oxygen. Okay. So, the overall complex or the overall ion is Si2O7 6 minus. Okay. This is SiO4 4 minus, this is Si2O7 6 minus. And then you can also have another kind of a structure, again a unit, a structural unit like this. Okay. So, this will also have a unsatisfied bonds at the outer surface or outside this ring, whereas this has only one bridging oxygen, whereas in the form of a ring it can have 3 different bridging oxygens. Okay. So, this is a isolated silicon oxygen tetrahedron, this is a 2 of them have combined together, and here 3 of them have been combined. This is one silicon, this is another silicon, and forming a ring. Okay. And these oxygen of course are still unsatisfied, the charges, and therefore, it has a net negative charge Si3O9. So, there are 1 oxygen, 1 silicon, 2 silicon and 3 silicon. So, these are the groups, the repeating groups one can have in different silicate structures. It can also have much larger rings, like 6 of them forming an hexagon kind of ring, a kind of benzene ring. Okay. So, this is silicon, 6 of the tetrahedron are joined together, and 6 of the oxygen are satisfied or been shared between 2 neighboring silicon ions, and therefore, there are 6 bridging oxygens and forming a hexagonal ring, and the net negative charge is 12 minus, Si6O18 12 minus. Okay. You can also have this kind of a chain. Okay. You can form a chain. Earlier we have seen two of them can be joined, and you can have Si2 Si2O7 6 minus. We have seen that. So, only one bridging oxygen, but this can be extended further. Instead of 2 you can have 3, 4 and go on, it can go on endlessly, just like a polymer chain. So, it is a kind of inorganic polymer chain as if. So, you can have SiO3 depending on the number of such units, you can have N, and the total charge, negative charge will be 2 N minus, and this particular kind of structure is known as pyroxene structures or pyroxene silicates. It is also possible as I said, there are very complex situations so far as the silicon oxygen network is concerned. It is some kind of a network with as if there is a polymerization with monomers. So, these are the units or monomers are getting together and forming a chain. Now, we have seen a single chain. Here there is a double chain. Okay, that means one chain is this one pyroxene chain is here, another pyroxene chain is also more or less parallel, but they are not isolated. They are connected. They are connected between these two chains as if there is a what we call a cross linking of polymers. So, this is one polymeric chain and this is another polymeric chain, and there is a cross linkage through a common oxygen ion. So, this silicon ion and this silicon ion sharing one particular oxygen, then this silicon ion and this silicon ion is sharing another oxygen, and once again there is a sharing of oxygen in the here again. You must notice that all the silicons are not sharing between the two chains. For example, this silicon and this silicon is not sharing, but this one is sharing. So, it is normally or the structural requirements or the requirements is that alternate silicon ions are actually sharing oxygen between them, and therefore, a bonding is taking place between the two parallel chains, and that kind of structures or the silicates are called amphibiols, and this is the unit Si4O11 which N 6 N minus, that is a simple calculation. Okay. So, amphibiols another variety of silicates. So, depending on the silicon oxygen arrangement, how the tetrahedron is shared between their neighbors, you have different kind of structures, different kind of properties, and of course, the different applications. This is in summary we have seen, you can see there are, if you the isolated silicon oxygen tetrahedron, these are called olivine structure, this is called beryl structure. Okay. There can be rings. I have given you 2 examples of 3 member ring, 6 member ring, but it can be a 4 member ring also. So, there are different compounds present, beryl, zeolite and bentonite. We will not be discussing too much about these things because they are basically falls in the traditional ceramics arena, and this course is on advanced ceramics. So, we will be discussing mostly on the advanced ceramic compounds, but silicates being one of the major constituents of ceramics, particularly traditional ceramics, just have a idea what are they. These are single chains pyroxenes we have discussed already, amphiboles, the double chain, this is one chain and this is another chain and forming a kind of hexagon in between. And then there is the next variety is called sheet silica, because there is a, it is a 2 chain, but if this extends in the other directions also, a large number of chain forming a basically a sheet structure, okay, a horizontal sheet structure. They are all in the form of a large number of chains, as if a large number of units have been put together in 2 different directions, x and y direction, not in the z direction. Z directions the bonding will be different, and we will see that later on how the z directions also gets bonded together. Normally these bonds, the z direction bonds are much weaker than the x y z direction bonds. So, this is what we call the silica structure, sheet silicate structure. Mica is one of the examples of this. So, arranging SiO4 tetrahedron in different silicates, the exception is in the sheet that extends indefinitely in all directions in the plane. So, these are the best known ways of combining or not combining the SiO4 tetrahedra. Okay. So, this is the different arrangements of SiO4 tetrahedra, which is the basic unit of the building block of all the silicate structures, and that building block is combined with the next building block in different patterns and different forms, and that is how we get different kind of silicates. Well, I think besides of course silicates, we have not discussed much about the pure silica. Silica as its on its own also is a very good important ceramic raw material, and it is not does not combine with others. It is called silica is basically a network structure where all the oxygen ions we have seen in earlier structures. You see all oxygens are not combining with silica. Okay. So, some of the oxygen is combining with silica, and the rest unfilled or unsatisfied bond has to be satisfied with other cations, which has not been discussed here. But in a silica, pure silica structure, all the oxygen will be a kind of bridging oxygen. That means only bond between silicon and oxygen, and that satisfies the complete charge compensation or charge neutrality, right. So, there is no other cation is needed for combining with oxygen, and therefore, in any silicate structure it is actually what we call a framework structure or network structure, and therefore, only oxygen and silicon satisfies all the bonds of silicon as well as oxygen, and therefore, you have a repeating unit of this kind of tetrahedrons. These are tetrahedrons, they are arranged. So, these are actually these molecules silicon oxygen molecules will form are arranged in a particular geometric pattern, and that actually gives you the complete silicate structure, silica structure SiO2. Now, there are different polymorphic forms of silica, we will discuss that maybe in the next class, and let us finish it here for the time being. Thank you so much.